Oh, I should probably start. Okay. Probably a good time to start, given that it's 9:30. Okay, so this week, remember, class, I'm supposed to try to pack everything into 45 minutes. So I will be zipping through, and then I'll address questions and stuff afterwards for like 15 minutes, and then I cram for my next class. Okay, so group theory, that's what we're doing for a long time. The topics for this week, because I know students want to know what's coming up, but it's kind of hard for me to say because I go kind of week by week based on where we ended up last week. So, okay, you need not Shungite, Shungite. You need blessings. Here you go. Here's your blessings. Okay, so the week's topics, though, for today, here's your Shungite. So for this week, the general types of topics, the general theory, the abstract stuff, will be these concepts. The concept of a homomorphism, an isomorphism, maybe the subgroup generated by a subset, the concept of subgroup generated by something. We've seen one example of that concept, but it's more general. And then the actual first theorem in group theory, the first non-baby theorem. The things we've already done don't really classify as theorems. But this one, Lagrange's theorem, is the biggest, most important thing, abstract thing that we learn this week. It's a great theorem in the theory of finite groups, and we'll use it a lot. We'll use it all the time. Okay. Okay. Next. So as far as concrete things go, concrete groups to focus on this week. Okay. Cyclic groups. I want you to just read about them in the book. Okay. So I'm not going to spend much time on them, but I'll just say they're all just like basically Z mod NZ or Z. Okay, I'm just gonna that's what they are, though we have a little discussion to be, there's a little bit of a discussion to be had that's actually about the concept of an isomorphism. So they're all isomorphic to Z mod NZ or Z. Okay, that's nothing really new. But the new groups that I want to introduce this week, and not just introduce, but really play around in and get a feel for, are the symmetric groups and SN. So that's what I want to do concretely, introduce you to this week. And then another concrete group, which is just fun for now, is going to be the group of symmetries of a three-dimensional shape, this time a tetrahedron. So one of these, a regular tetrahedron. All of them, all the sides are equilateral triangles. The rotational symmetries of that type of a shape, that's a group, and we'll try to understand that group if we have spare time, just as a fun other example, new example. Okay, so for today, what I'm going to do is tell you introduce the definition of what a homomorphism is, and then a special kind of homomorphism is an isomorphism. It's like vocabulary. It's like part of the language of group theory. So that's how you want to think of it. The second thing is I'll just state Lagrange's theorem to tell you what our goal is in that theorem. Lagrange's theorem has nothing to do with homomorphisms and isomorphisms. We're doing two parallel abstract things. Okay, so Lagrange's theorem is its own little segment this week, and then at the end we'll do concrete stuff, like I'll show you what the group Sn is as a object, and then we'll multiply two elements and see what it feels like. Okay, so the symmetric groups these are called the symmetric groups, or the permutation groups. are absolutely one of the most important classes of groups, examples of groups that everybody needs to know. Okay? All right. So that's great. So we have a good week coming up, and so let's begin. I need to tell you what a group homomorphism is. Okay. So here's a definition. It's going to be nice and abstract. It's going to be dry, so that means we need to put some music on, which is boring music, but whatever. Okay, so definition. Okay, so we have the following setting. So before we have the definition, we have the following setting. We have one group G, and I'm going to denote its multiplication by dot. And we have another group G prime. Two groups. Oh, and its multiplication is going to be denoted by, let's say, little asterisk, little star. Okay? They have two groups. All right, so the definition is this. A group homomorphism from G to G prime is first of all just a function. From G to G prime. Okay? Which, what we say, the language is which respects the group laws. Which, and this is a phrase, this is how we say what I'm going to write next, which respects the group structure, group structures. And what that means is, for any two elements A and B in the domain, if you do A times B in the group G, and then you see what F sends it to, it's the same as if you did output number 1 times in the output in the other group, output number 2. This kind of a thing where you're studying a particular class of objects which have a structure on them. Here we have a group structure, a law, a group law, a multiplication law. And you're trying to like understand the relationships between different objects of this type. You'll see that we typically want to respect the extra structure. We don't want random maps between two groups because that's just that collection of functions is itself too floppy. It's not transporting faithfully the multiplication. It's not aligning the multiplication tables together. It's not playing with this extra structure. It's kind of ignoring the extra structure. So we try to like narrow down to functions between objects which play well with the extra structures that we are playing with in the first place. And the extra structure we're talking about is the group law. Okay, so what is the role that homomorphisms play? Okay, so why do we have this definition? So why? So I'm going to introduce you to a grand conspiracy. A grand conspiracy. In other words, what this is a way of framing a lot of your current and future math classes. Current and future math classes. It's a way of kind of situating yourself in lots of subjects in math. In fact, most of them. All right. The grand conspiracy is, in a bunch of math classes, you'll find that the semester or the course focuses on two aspects. You'll see you'll get introduced to the objects that you're studying. For us, groups right now. You'll get introduced to those first. And then, the next week, you'll get introduced to the relationships between those objects. And then, crucially, the relationships among all the different objects that you're studying. Between objects. Or among the objects. Okay? And what this group homomorphism concept is the relationship part. We're now talking about when you have two groups, we're specifying a particularly nice collection of functions from one group to the other, the ones that play well with the group structures on either side. Okay? And group homomorphisms are the tool by which we can start to say how one group is related to another. Is there a group homomorphism from one group to another? That in our minds we think of as some vague concept of a relationship that one group has with another. Okay, so that's the idea. And I'm going to tell you a particular special kind of homomorphism has a particular special kind of name. So here's definition number 2. Definition. A homomorphism is an isomorphism if it is bijective. In other words, it's a perfect one-to-one onto mapping between G and G prime. All elements of G prime are exactly hit exactly once by an element in G. The elements of G and the elements of G prime are like partnered up in such a way that when you multiply on G's side, the partners multiply correctly on G prime's side. The multiplication on both sides are in alignment. That's what this group homomorphism property means. Okay, what if my G is antisocial who hates group structures? Actually, every group affords homomorphisms out of it. Sometimes they're silly. So let's do some examples. Immediately, every time you see a definition in abstract algebra, you should realize that it's not very abstract because it's built off of experience. Huge, vast conspiracy type of experience. Okay, so examples. Immediately, you jump to examples. This is a game you should play personally. Okay, every time a definition shows up. All right, so we start with just stupid examples. Stupid examples. The stupidest example. Okay. All right. Been doing 10 hours of math? I don't know what that means. Okay. So, that's the time. That's the local time. Okay. So, stupidest example. This is an example of a homomorphism that exists between any two groups. So let's call it S for silly. Here's the rule. Every element gets sent to the identity element in G prime. Let's call that E prime. Yeah, this is the identity element. Send everything to the identity element. Okay. Why is Why is this a group homomorphism? Okay, we have to check. S of G times H. Okay? S of G times H equals, by the rule, so the rule equals E prime. Okay, that's what it is on the one hand. On the other hand, S of G times S of H is, well, by the rule, this is identity. And by the rule, by the name of the homomorphism, this is also identity. Oh, so that's identity. Yeah, done. Okay, so these are the same. Great. Stupid. It's called the trivial homomorphism. Called the trivial. The trivial homomorphism. Okay. Okay, let's get rid of that. Okay, that's great. Okay. Here's another example that's kind of also trivial in the sense always there and maybe not worth talking about, but we should probably give it a name. So here's another example, the identity homomorphism. So it's called identity, and it goes from a group to itself. Okay, and the name is G goes to G. Okay. I'm not even gonna check that this is a group homomorphism. You can do that yourself. This is silly. All right. Okay, so that's great. Now, let's do some actual examples. Okay, here's an example. Exp from the additive group of real numbers to the multiplicative group of real numbers. Okay, I'll just write it. I'll just do this. Non-zero real numbers with multiplication. All right. So this is a group homomorphism. What is it? What is the formula? Exp of a number is, by definition, just this, or 2 to the x, or 3, or another one, or you can also do, or a different one. You can do 2 to the x or something. Okay? That is a group homomorphism. Because e to the x plus y is e to the x times e to the y. And this rule is just the fundamental respecting the two group laws. Okay? Now I want to say something. This homomorphism, as it currently is written, is right now not an isomorphism. Because as I've written this, the negative real numbers are never hit as e to the x, right? It's not surjective. It's not surjective. Okay, so we can tweak it a little bit. So let's do, but this function the positive real numbers with multiplication as the group, this same exact formula, this is an isomorphism. Okay, so what does isomorphism mean? Isomorphism means that one group with its group law is, in effect, a carbon copy of the other group with its group law. Even though they literally don't look the same, the isomorphism gives you a Rosetta Stone that translates mathematics in one group perfectly, one-to-one, in perfect correspondence with the other mathematics, the other group structure in the other group. One group might involve apples, the other one might involve oranges, but they might be isomorphic, which is this, to say that the essential structure is common to both of them. They're just manifesting in two different ways. That's how you want to think of an isomorphism between two groups. Okay, so this is a funny example. There's all kinds of homomorphisms in the world. There's all kinds. There are all kinds. Among groups. All kinds of homomorphisms, meaning out there, just not necessarily among two given groups, but if you let yourself choose two groups, you can find lots of isomorphisms, examples of homomorphisms out in the wild. Okay, so let me show you another one, e.g. The thing called determinant was a group homomorphism. GL2 or GL3 even. To the multiplicative group of real numbers given by a matrix M goes to its determinant. That was a group homomorphism. And what we're saying is that the determinant of the product of two matrices was by a massive algebra calculation. Miraculously, it was the determinant of M times the determinant of N. This formula is saying that the determinant operation is a homomorphism from the matrices to the non-zero numbers. Okay, this homomorphism, by the way, this homomorphism is surjective. That is surjective, but not injective. Okay, go ahead and convince yourself that the determinant is not injective. All right. Okay, all kinds. So determinant was a group homomorphism. Let's do something else. Here's something. Something to think about for now, because I have to switch topics just first, because 45 minutes. But there are no non-trivial homomorphisms from Z mod NZ to Z. Okay, so that's something to think about. The real question is, like, where would you have to send? Where can you send the generator or the element bracket 1 in Z mod NZ? Where can it go? Because wherever it goes, use the group, preserving the group structure formula to deduce, where is it? To deduce, use it many times, use it like n times in succession to deduce that the element 1 could only go to the number 0. There was no other option for constructing a homomorphism from Z mod NZ to Z. But here's the second thing. There are non-trivial homomorphisms from Z to Z mod NZ. For example, a number gets sent to its K gets sent to its equivalence class. That's actually a homomorphism between the two, from Z to Z mod NZ. So you can have non-trivial homomorphisms one way, but only trivial homomorphisms another way. So it's like homomorphisms are not, the existence of homomorphisms is not like a perfect two-way street. Some groups map to others easily with lots of flexibility, and some groups don't. They're resistant to mapping into other groups. They are antisocial. Okay? Great. So enough about homomorphisms and isomorphisms right now. I'll leave you with this question. In your huge list, all groups I know, start drawing a little chart, you know, like a detective does with those strings. Like, put all the groups you know on the wall, like put them on the wall, and start drawing strings between them if they are isomorphic. Okay, so in your list of groups you know, look for all isomorphisms. Look for isomorphisms among them. Because that's what we mean when we say one group is spiritually the same as the other group, even though literally their definitions were different. Their contexts were different. They arose in different stories. But still, there was a Rosetta Stone between the two groups. So look for as many isomorphisms among your groups that you can, because that means that those two examples were secretly the same example, up to isomorphism. So go and do that. It's a great exercise. We'll do lots of it once I have time, maybe after the lecture, if you have questions about that. Okay, so we move on to the next third of the lecture, which is, I just want to state the marvelous theorem of Lagrange. All right. Okay, so next topic, topic change. Or for now, we'll go back to homomorphisms next class and prove simple little baby theorems about them and so on. But topic change, Lagrange's theorem. So the marvelous theorem of Lagrange. Let me state it. Let me state the theorem. If G is a finite group, it's a theorem about finite groups. G is a finite group, and if H is a subgroup, it's a theorem about finite groups and their subgroups. Not a subset, a subgroup. Then, the size of H always perfectly divides the size of G. Okay, too many vertical lines, but it says the size of a subgroup, the order, let's use the language, folks, of a subgroup divides the size, order of the whole group. All right, so there's some kind of divisibility type of mathematics that comes naturally in the study of finite groups. And you'll start to see in group theory a lot of interesting theorems that like assume that the group has order a prime number or a power of a prime number. Prime numbers start to become kind of relevant in more advanced group theory theorems and curriculum. And the real reason why it's happening is because Lagrange's theorem is saying that divisibility pops up naturally when studying subgroups of a given group. And you can understand a given group by kind of looking at the relative position of certain naturally assigned subgroups of that group. For example, the center was one example that we that naturally happens in a group, naturally in every group. So divisibility is born as a sort of important thing to pay attention to, an important little tool to exploit, thanks to Lagrange's theorem. All right, so here's the first thing you should do now that I've stated Lagrange's theorem. What you should do, class, verify this with as many finite groups that you know. Okay, so you have a big bag of groups now. Finite groups. Maybe that's not that big, actually. I think you have at least Z mod NZ. You have the dihedral groups. Let me show you another collection of finite groups that you have. So let me expand your bag real fast. I'll expand your group bag with a cheap trick. If you have two groups, you can create a third group in a cheap way. It's called the product group. It's the set of the group, underlying set, is ordered pairs. An element of G, comma, an element of G prime. Okay? The group structure is parallel computation. The operation is, if this is star and this is dot, the operation is this. So like G1 comma G1 prime times G2 comma G2 prime is this pair. You just operate in parallel computation, separated by comma. The new group, and if G and G prime were finite, G cross G prime, another finite group. Look, your list just exploded. And now you could go and explore that huge infinity squared collection of examples and test everything you want to test against those examples, okay? You can take the product 3 times. Oh my god, you just cubed, infinity cube examples. Wow. And then you can take the product 10 times of different groups. 10 different groups. Incredible. You know so many groups now. Go and test every one of our theorems against those groups. Okay, no problem, Martian Robonaut, no problem. Okay, so by the way, the identity element here is E comma E prime is identity. And like G inverse comma G prime's inverse. That's the inverse of G comma G prime. It's parallel computation forms another group. Great. Fascinating. Okay. And as you know, class, I really like testing explicit playing around and fiddling around in examples. You know this from the traumatic exam you just had yesterday, though the class did fine. I mean, the class did, like, no one did disastrously. So so the exam was actually at a good level. But you notice I like testing real understanding of concrete fiddling. Like, does the person know? Or is it just words to this person? Is it just words? Or is there some huge chunk of examples that they can draw from in their mind and they're fluent with? Good. So go and test definitions against our now insanely huge list of groups, thanks to the product operation. Okay, that's Lagrange's theorem. There's a divisibility conspiracy for subgroups inside of larger groups. Okay, so the last thing I want to do is introduce a new group that you haven't seen yet. Okay, that's the symmetric groups. the last topic today. Last thing for today is I want to introduce you to my friend, the permutation groups. A new collection of groups. They're all finite, okay? New, very important. Okay, and these are called the permutation groups or the symmetric groups. It sucks that we use the word symmetric groups because maybe you would think that should be the dihedral group because that's the symmetries of it. No, but whatever. So they're called the symmetric groups or the permutation groups. And there's one for every integer bigger than or equal to 1. Okay? So here they are. Here's how the definition is this. Definition. You start with a set that has n elements. And the one that we always start with the most common choice, the exact set doesn't matter. The choice we make is the set of numbers from 1 to n. Like you just start with the fact that they're numbers is not important. Just n, an element that has n, a set that has n elements. Okay, start with this, okay? And now, the group is the following. Sn is, by definition, check this out, it's this. It's the collection of all bijections from this set to itself. P is a bijection. What is a bijection of a set with n elements with itself? Let's look at it really carefully. If you draw it, let's say n is 3. Let's draw a picture with n equals 3. Okay, two sets. And the elements are named 1, 2, and 3. What does a bijection look like? It's a function, so you got to start assigning arrows, input, output. But it has to be 1 to 1 and on 2. So there can't be two arrows colliding, and in fact, for finite sets, you just can't have two arrows colliding because surjective between a finite set and itself implies injective, but whatever. Okay, so here we go. Here's an example. And now, you see how this bijection, it encodes a permutation of the elements. Namely, the element called 1 was sort of sent to 2's position, and 2 was sent to 1's position. You think of it, you can visualize this function as inducing a jumbling, a permutation of the numbers 1, 2, and 3. The arrows are assigning like where does this element get jumbled to? Like where does it what's its new location? That's how you can think of the arrows, what the assignment of the arrows is. No two inputs map to the same one because that wouldn't be a bijection. Okay, so Sn as a set is the collection of all conceivable bijections of this set with itself. And I think of a bijection as a permutation of the set by drawing the arrow picture. Okay? So, but that's a set. Right now, that's just a set. I'm claiming that Sn forms a group under some kind of operation. So this is a set right now. The group structure, the group law, is composition of functions. Okay? So here's the point. If you have one bijection from a set to itself, and then if you have another one another input output function, which is a bijection, then what's called P then Q, right? You first do this, and then second you do that. So that's why you put P first. First from the right? Because we put inputs of functions on the right hand side. F of x, that's what we do in the United States. We don't do x of f, which you might find in some strange corners of Europe. Okay, so that's this composite is Q, P then Q, but it's written Q composed with P like that. Okay, so this is, again, a bijection. Because of the following general, simple thing to prove. The composition of bijections is again a bijection. Okay? All right. Okay, thanks, Ellipse, whatever. Okay, so, but look, right now, so that defines a binary operation. Composition of functions is just in this whole universe, in all contexts. The composition of functions is an associative operation. If you have 3 functions stacked in a row, you can clump them as the first 2 first, compose, and then do the third. You get the same result as if you clump them the other way. But not if you swap the order. No, that's not what I'm saying. I'm saying clustering 2 out of 3. Okay, so this is associative because composition of functions is associative. All right. There is an identity element. It's called the identity function, which is always there when you have a set and you're looking at maps from the set to itself. You just send I to itself. You know yourself. Know thyself. It's identity. That's why it's called identity. All right? That thing, you compose it with any function, you get the original function back. Very simple. Okay. So I'll write that. P composed with identity equals identity composed with P equals P for any. Okay. Awesome. Okay. Next, inverses. Okay. Inverses exist because if you have a function that's a bijection, then there is a function that goes the other way, backwards. Which undoes f. Okay, so there's which when you compose both ways, you get identity on A and on B. All right, how do you define this inverse? G of an element is the unique element that was sent to B under F? That's always available. When you have a bijection, you can undo it with the function. And it's called, this is the recipe for that undoing function, right? In the same way that, like, multiplication, squaring and square root, and what, that's a bad example. Whatever. You know what I'm talking, you should know what I'm talking about from 3613. Okay, so there's your group Sn. It's the set of permutations where we view a permutation as a function from the set to itself. You think of the function as a scrambling of the set. Okay, like if you can see the scramble with these arrows, that's why it's a permutation. That's what we mean. You have the right intuition. This permutation swaps 1 and 2 and keeps 3 untouched. That's what this permutation does. Okay. Okay. So, no. Lactose intolerant. We're gonna talk about finite sets here, so we don't need to. I know what you're talking about. We don't need to worry about that kind of stuff. Okay. So, okay. Okay, so that's the group Sn, and now the question is, basic questions that we have to figure out. How big is How big is Sn? What kinds of subgroups does Sn have? Now you might think, well, that's a kind of crazy question, but I just want you to get your hands dirty with like S1. Okay, S1 is very simple, silly group. S1 is the identity group, the most trivial group in the universe. S2 is also kind of silly, but let's just get our hands dirty with just the first couple symmetric groups. Play around in them, try to compose elements and come up with a system of how to label elements. That itself is a little bit of a story that I have to tell you. So what are some subgroups of Sn? Try to get some understanding of that. The reason why this is a fascinating question is, I'll tell you something. I'll warn you. This will be shocking to anybody who hasn't seen this before. Every finite group in the whole universe, every single one is isomorphic to some subgroup of some symmetric group. So the symmetric groups are kind of the home of every finite group conceivable, ambient home. They secretly. So when I said what are subgroups of Sn, if I asked you what are all the subgroups of Sn, the answer is amazing. It's just every conceivable finite group that's the list, and there is no list like that in the universe. No one has a list of every single conceivable finite group. It's such a wild zoo of them out there. Okay, so that's the new little group that we introduced, and you have to go now today and start playing around in S3. Say, just start. Look how many elements does Sn have? See if you can find a pattern. We'll establish these once and for all in the next time we do concrete things on Wednesday. But you should play around with it on your own. Is there an uncountably infinite number of finite groups? Actually, I believe that it's countable. Yeah, I believe it's countable because for each size, when you specify a size, there's finitely many group structures, groups of that size. But then, so you have a countable union of finite sets. So that's a countable set, or countable. Yeah, you're modding out by isomorphism. Yeah, right. So you should remember that a countable union of countable sets is countable. A great trick from set theory. So, what else? Any reason why S0 can't exist? Actually, S0 exists. S0 exists. Yeah, because the empty set is a set. And yeah, exactly. The empty set is a set. And so there's an identity function on every set with the same rule. It's the same rule works. So yeah. So S0 actually has one element, is also the trivial. And this is saying, this, by the way, students are probably gone by now, so students can all leave. But you know, how big is Sn? It's n factorial will be the formula. And that's also the number of permutations that you learn in high school, and of course it's all related. So it's the same statement. So, but you might have seen that 0 factorial is taken to be 1. But at first you might say that's just a convention, but like S0 has one element called the identity function. So, and it's invertible because identity composed with identity is identity. So if you think of n factorial as the cardinality of Sn, it'll actually give you a justification for a bijective proof for why 0 factorial is 1. So yeah, all you have to believe in is the empty set as a set, but that's why 0 factorial is 1. Okay. Anyway, the textbook is I'm just using it for continuity's purposes because that's what was used in the past, and I don't want to upset anyone or whatever. So we're using something called Contemporary Abstract Algebra by Gallian. It's not like Dummett and Foote or some of the more standard ones, I guess. But it's good. It has a lot of like examples and large discussions about what the various concepts mean, more than you'd find in some of the more direct, short, terse books. They're the ones that I learned from. Oh, really? Oh, that's cool. That's cool. Great. So there's like precedent. I don't know. I don't know what the consensus, like what the best algebra books out there are, but yeah, I had a traumatic experience learning algebra, meaning my first intro to algebra was Lang's algebra because I thought I was like cool or something, or I hung around a lot of grad students and they were taking this Lang's algebra. And no, I didn't have like a traumatic experience, like it was hard. It was I went straight to one of the most dry sources. But then after that, like, I became way better at algebra. But it was like, you know what I mean by Lang's. What's up with Lang's algebra? It's like I think, I don't know. I don't know if you've ever seen how he defines the polynomial ring in one variable. It's like the set of all functions from the free monoid on one generator to a ring R. It's like the set of all functions from a free monoid to a ring R. It's like, I mean, I get why you had to do that, but it's pretty dry. Yeah, pick up a homological algebra book and prove all the theorems yourself. That's actually terrible. Like, homological algebra can get really complicated. So it's not at all something to dismiss. And getting a strong foundation in homological algebra is like very important in higher mathematics and should not be minimized. It's not some obvious. Extant Tor functors are not just, oh yeah, easy, just abstract nonsense. Well, no. They're complicated. That's hard to compute them, and you got to get your hands dirty. So, yeah, that comment is hilariously misguided. But anyway, so yeah. Let's see my Discord. Maybe I wonder if there was any activity happening in the Discord for the class, whether people had questions. There was just an exam earlier. Yeah. Okay. So, right. So, the class, I don't think I need to respond here, but in the Discord, you're having a great discussion, and you should continue having very robust discussion on the material, because I learned the most out of other people. The bandwidth between human beings is there's much more bandwidth than between a book and a person. It's kind of, you can get information across much faster. So students should definitely use the Discord heavily, but not during the exam, of course. And now you know what kinds of exams I like to give. I like to give an assortment of freebies. I'm sure a lot of them are freebies for you. They better be. And then there are some medium ones where I ask you to just compute something or check something. And then there are some trickier ones where you have to get your hands dirty. You have to try examples and so on. And I'll give a good range every week. And remember, I have to come up with exams that are not checkable. So, but I won't go crazy. I won't go nuts. I'll stay within the confines of the type of the groups and examples that we mostly talk about. Okay. Yeah, no, Discord's only for students. I can't open that up. See you in the next century. That's right, Diado. Oh, analysis gang. Yeah, there's all kinds of new people here. Lactose intolerable, non-dairy. Oh, let's see. Thank you to, yeah, Lactose Intolerable for following. Jeeves Zero, Zeta Wop, Dadun, Data, Dude, SpaceX, Jedi. Wow, amazing. N not M, thank you, you just followed. I hate mid Smurfs, okay. Varric Tan, Adderall Anderson, wow. Vienna, Starch Face, okay, those are old. Yeah, so thanks. But it's 10:30 now, and you all know what that means. That means I have to go make up a BS lecture for Calc 2. Happens in an hour. So I'm gonna have to send you all somewhere educational. It's been fun. Thanks for tolerating my one-pointedness during the lectures. Remember that we are forced into 45-minute lectures, which is complete garbage. I don't understand this, but we have to do it. And so I have to stay, I can't get triggered by chat like I usually do. But you guys are good. You guys have been respectful of the situation. RB tree. Okay, you want Shungite? Okay. You want Shungite? Okay, Diana, we'll go over there. We'll go over there. Thanks for suggesting that. That sounds cool. Here's your Shungite. Ellipse. You redeemed it. Oh, you need 3. 1, 2, 3. Okay. Alright, awesome. Okay, Tropical. Then you should redeem it with your channel points. It doesn't cost money. It's just a little thing on the bottom of your chat that's... I don't know. It's just dumb. It's dumb. It's dumb. Just a dumb thing. If you want a Tesseract. Okay, I don't think I have a Tesseract on me. You know, it's hard to hold. It's kind of harder to hold the Tesseract. Yeah, you'll have to give me some. You'll have to give me some time. You have to give me a little bit of time. Artia Hiko. Give me time for the Tesseract. Okay. What's a teacher's pet? Teacher's pet is, you know, the student that like tries like is like the best, and like the teacher loves that student because they are just saying great things all the time, and that student can just never do anything wrong. You know that student. It's like obnoxious and like sits in the very front and smiling all the time. Yeah, that's teacher's pet. So okay, but I have to guys, I have to like learn Calc 2 in 1 hour. What am I gonna do? So I and get nutrients, because that's I have to do that. So, oh, what's that emote? Thank egg. Thank egg. Wait, I don't know, what is that? Oh, is that a person? Oh, that's a person like kneeling or something. Oh, thanks, virtual assistant, for following. Welcome. Okay. I couldn't. It looked like a helmet. I don't know. Does it look like a helmet to anyone else? Like a motorcycle helmet? But I'm a boomer. Maybe. Big substitution, Roosta. Absolutely. That's what's up next. Snail. Okay. Yes. N not M. Yeah. Snail. That's what. Exactly. Snail. I don't know. One day I'll probably do emotes here. You are not a bummer. Boomer. Bummer. I am a bummer too, but like I'm both. Oh yeah. But you know, yeah. But in the gaming world, if you're like over 25, you're a boomer, basically. All right. Oh yeah, ellipse. Thank you. Yeah. So sorry about that, Artia Pico. Oh wait, what? What is that? Oh my god, my wife is nagging me. Oh my god, I gotta go fix the house. Oh no, I'm gonna have to go. Yeah, okay, honey, I'm coming. Yes, I'm coming. Yeah. Yeah, okay, yeah.